Good evening and welcome to the second installment of Adventures in Particle Physics, coming to you live from the University of Stavanger, Norway. My name is Alexander Rotkopf. I'm a physicist here at the University of Stavanger and I'll be your host for this evening. This week, the Institute for Mathematics and Physics at the University of Stavanger is hosting a virtual physics conference with more than 300 participants and around 150 presentations of new scientific findings in experimental and theoretical fundamental physics. This research is made possible through your taxes, and we are aware of the responsibility that comes with your trust. As scientists and teachers, we wish to share with you what kind of physics research is discussed at this conference, and to do so, we've prepared 3 inspiring presentations for you this week. The first one took place on Monday, we have one tonight, and there will be a third one on Friday, August 6th. The speakers are physicists who would like to share with you some of their insights and fascination for the study of the microscopic building blocks of the universe and the forces that tie them together. If you have questions or comments during the presentation, feel free to leave them in the live chat window that is right next to this YouTube video. I will be collecting your questions and comments, and together with the speaker, we will get back to you at the end of the presentation, so stay tuned until the very end for a live Q&A session. The video that you're watching is a 360-degree virtual reality video, and you can adjust the orientation and the viewpoint by clicking on it and dragging it. Note that you can find a copy of the presentation linked in the description of this video. Our speaker tonight, Chris Quigg, is a veteran of theoretical particle physics and of science outreach for the general public. In his career at the Fermi National Laboratory in the United States, one of the US's premier particle physics laboratories, Chris has worked on many different topics in particle theory. Not only has he helped to better understand the properties of particles that were already observed, but he actually helped to plan and develop new experiments to hunt for particles that were not yet observed but theoretically predicted. As it is customary for successful physicists, Chris has worked with and at many international institutions. For example, the University of Berkeley in the United States, the CERN laboratory in Switzerland, and the École Normale Supérieure in Paris, France. For his work, Chris has garnered multiple prizes from scientific organizations. And tonight, Chris will present to us some of the remarkable insights that physicists took into nature, and he will share with us what are symmetries and how they help us to understand the nature around us. And with that, Chris, please, the virtual stage is yours.
Well, good evening. Thank you for that generous introduction, Alexander. And for all of you who have joined us, thank you for being here. As Alexander indicated, we who do physics research are very lucky to be explorers. And one of the great delights of being an explorer is to be able to come home and to tell our friends and neighbors what we've seen and what new questions we have. And I'm going to try to share some of that with you tonight. I would like to be with you in Stavanger. I am, as you see in this segment of the globe, I'm actually very close to Chicago, so several thousand kilometers away. But through the miracles of modern technology, we're able to be almost together, at least in 2 dimensions. It's a particular privilege to talk about symmetries tonight because Norway is the home, the birthplace of 2 of the founders of the mathematical formulation of symmetries. Niels Henrik Abel, who was a local boy as they say, originated very close to Stavanger. And a little bit later, Sophus Lee, who gave rise directly to the kinds of mathematical formulations that we use to try to make sense of nature by applying symmetries to them. So I'm happy to pay tribute to those local people. And all of us, of course, in mathematics and physics have benefited from their insights and built upon their insights. All of us have, I think, a rough knowledge and understanding at some operational level of what symmetry means. Part of what makes us alert people who are paying attention to our surroundings, is that we seem pre-programmed to try to find patterns in our surroundings, in nature, and other things that we look at. Here is an example of a decoration in the Ludwigskirche in Munich. It's a rather intricate decoration in a dome in one of the side chapels in that church in Munich near the university. And if you look at it, you will see that there are many regularities that we recognize. You'll see that if we take the whole decoration and rotate it by 90 degrees, a quarter of a turn, it looks the same. You can keep doing that once, twice, many times. If you look at different elements of it, you will see that they too reproduce themselves under certain reflections or rotations. And it's natural that our eye is drawn to these. And when we're looking at them, we're not only taken in by the colors and the pattern, but we try to project onto those an understanding of what are the elements, what are the similarities that make it something that is an appealing decoration. So keep that in mind, and we'll try to give some more formal definitions of what we mean by symmetries, and a couple of examples of how we begin to use them to enhance our understanding of nature. If we look to more formal definitions of symmetry, what we mean in mathematics and in the applications to science is something that is indistinguishable, two things that are indistinguishable. So if we take the drawing that we just looked at it and look at it before and after a 90-degree rotation, it looks identical. So that indistinguishability in a pattern, in an equation, is what we mean formally by a symmetry. Off to the side, and related, very important in the arts of decoration and in trying to recognize patterns in nature, we can notice that some things may not be quite identical, but you can see how one is related to another before and after what we call a symmetry operation, by which we just mean looking at it from a different point of view, or turning it or reflecting it or doing something to it. So that's pretty straightforward, although a little bit formal sounding. What's a little bit more surprising to us who are grown up on raised on elementary ideas of symmetry that we learn in school and from our friends and so on, is that symmetry actually corresponds to disorder. It's natural for us, as in the example we just looked at, to think of symmetry as having to do with a certain order in a pattern. But that order often will actually reflect not a full symmetry or a perfect symmetry, but only a reduced symmetry, a partial symmetry. And that's something that I'll try to explain and help all of us be alert to in some of the examples that I give below. And then finally, the most obscure, perhaps, aspect of a symmetry is what we call in physics an unobservable. Observables are quantities that we can measure. So it can be the mass of an object, the speed of an object, things like that. But an unobservable is something that would not be measurable or would not give us a value if the symmetry held. And because that's rather obscure and not something that we encounter in everyday life, I will give at least one example of that so we can see how the notion of an unobservable, which might become observable, tells us something about the presence or absence of a symmetry. So let's go a little further. One of the early disciples in physics of Sophus Lee was a German physicist named Hermann Weyl. He worked first in Leipzig in Germany and then moved during the Second World War to the Institute for Advanced Study in Princeton. He was fascinated with symmetries all of his life and was one of the first to make coherent applications of the ideas of symmetry to solving problems in physics. He also was fascinated with the notion of symmetry as something that we see in various aspects of nature and decoration. Near the end of his career, he wrote a nice little book called Symmetry, which you see pictured there. It's available still in bookstores now in a new edition. And in that, he talks about some forms of symmetry that are particularly thrilling to him to illustrate. Those are the four categories I listed on the right. So mirror symmetry or bilateral symmetry. I'll show examples of these in just a moment. Reflection symmetry that we see in the reflection symmetry or near reflection symmetry of human bodies is one of the first things we're acquainted with. Translational, which means shifting, and rotational symmetry, which means turning. We'll see examples of those. Ornamental symmetry in wallpapers or in Islamic decorations, which can be fantastically intricate, often in 2 dimensions on plane surfaces, and the notion of crystals and examining crystal structure and seeing the beautiful regularities that those display. So let's look indeed at a few examples of these. First, I would call your attention to this object, which I think does not exist in nature. It's related to the human hand. One might speculate that in a few generations, if our young people continue to text at a rapid pace, this might be a beneficial evolution of the human hand to be able to text with 2 thumbs on one hand. But it doesn't exist so far, as far as I know, except in trick photography. It's if you turn it upside down, look at it upside down, it is a symbol in Middle Eastern cultures of an amulet, a talisman against evil spirits or evil eyes. So it is something that appears frequently in Western decoration or Middle Eastern decoration, though not directly in nature. So that's a reflection symmetry, a bilateral symmetry. Near the top, I've shown a translational symmetry. Imagine this lintel from a temple to be infinite in its extent. And then if we shift it by 1 unit or 2 units or n units or 1,000 units, it would look identical. So that's an example of a translational symmetry. And such symmetries are very common in architectural ornamentation. So that's reflection and translation. The next symmetry is a rotational symmetry, and here I've shown an example of it in what looks like the skeleton of a soccer ball, a football, but which is actually a representation of a molecule made of 60 carbon nuclei. It's something that's called Buckminster fullerene after the invention of geodesic domes and such things. If you look at this, you can see that if you make a diagonal that goes through the center of one of the hexagons and you turn it by a certain amount, the picture will look the same. Also, if you look at the pentagonal pieces, you can draw a diameter through that and rotate it by certain amounts. So that's an example of rotational symmetry, something that looks the same as long as you make rotations by a certain fixed amount. Here at the bottom is an example of Islamic decoration from the Alhambra in Granada in Spain. You can see that there are many things that you can do to that pattern to make it look the same. Again, on the assumption that it's infinite in extent and we don't have to worry about the boundaries of it, but there are rotations, there are reflections, there are slides from here to there. And that's part of what makes this kind of decoration so appealing, because it has multiple aspects to it. And finally, here is a simple crystal. This is cesium iodide, something that, as it happens, is used frequently for detectors in particle physics experiments, in which you have a structured alignment of the cesium atoms and of the iodine atoms, all quite regular. And this looks the same if you make certain rotations by, in this case, 90 degrees, or if you make certain shifts by 1 unit of the atomic species. So those are simple examples of symmetry, some of which we can see with our naked eyes, some of which we need advanced instrumentation to actually perceive. It's not simply in art or decoration that we see music. That we see examples of symmetry. Here's a famous example from music from the works of Johann Sebastian Bach. This is what's called in English the Crab Canon from the Musical Offering. And if you look at this, if you are a reader of music, you may recognize that the first voice is played backwards in the second voice. So the first 2 notes which are up here are reflected in the last 2 notes that are here. This is harmonious when played together, and the whole canon gives you a feeling for that. So, whether this is a little parlor trick by Bach or a deep appeal to our sensibilities is for the hearer of the music to decide, but it is an example of a symmetry. It's kind of a reflection symmetry with an inversion of the 2 voices. Okay, all of those have been symmetries that are discrete symmetries in the sense that they call for particular rotations or translations by a given unit. There are also some continuous symmetries. The prototype of those is a globe or a sphere. The sphere looks the same from any viewpoint. You can draw any diameter through it and rotate it by any amount or about any of those diameters, and it will look the same. So that's ancients regarded as the perfect object, the perfect symmetry, because it had this high degree of symmetry. And continuous symmetries, which are the ones pioneered in the mathematical sense by Sophus Lee, are indeed of great and central importance in our application of symmetries to physics, although the discrete symmetries are not to be dismissed. On the right, there is what I wish were an artist's representation, but it's my representation of the inside of a cloud. And there you can see that to some approximation, you can shift by any amount. You can move forward, backward, up, down, left, right, and it always looks the same. So that's another continuous symmetry, this idea of sameness. Now, what I'm showing you here are renderings of objects that display the symmetries. When we apply these to physics, sometimes it is the objects themselves whose symmetry attracts our attention and that we're able to use. And sometimes it's the equations that we devise to describe certain aspects of physics that have their own symmetries, often expressed in a mathematical sense. So let me now begin to move on to some of the applications of these symmetries or the ways that we think about them. All of us going about the everyday world make observations on our experience, and we try to generalize from our experience. If we promote these to be observations on the laws of nature, both in everyday experience and particularly when we make detailed quantitative studies on various physical phenomena, we may abstract from our experience that there is no preferred location or time for the laws of nature, that they're the same within our experience everywhere in time and space, and that there's no preferred orientation. The basic laws of physics, of electromagnetism, for example, don't distinguish between left and right, up and down, forward and backward. And so it is a temptation to take those observations, to abstract from them, and to see whether by applying those observations, we can learn constraints or guides to how to formulate specific laws of nature. In 1918, that problem was solved in a very complete and definite manner by this young woman at the time, Emmy Noether, who was a German mathematician, in a famous paper that had to do with invariant variation problems. So there it is in the original. Here it is in the English translation. And you see that what she's done is to combine the methods of the calculus of variations, a way of dealing with problems of mechanics and others, with Sophus Lee's theory of groups. And I've shown a recent Norwegian hero on the side to indicate that the two theorems she proved and the consequences of those are, as expressed here, truly astonishing in their application and in what they've enabled us to do. Like many things in the history of science, mathematics and physics, her paper was ahead of its time. And so the full implications of it, even though it was published in 1918, were not realized until the 1950s. And they have grown into one of the fundamental pillars on which we build our theories of the basic interactions of nature. Early on, in fact, in the context of her paper, she found that there were interesting and general connections between symmetries, these invariance principles, things that don't change, and conservation laws that, again, had been recognized as empirical regularities, as rules that didn't come from anywhere, but seemed to be useful for trying to describe nature. And through her first theorem, you can show that the idea that the laws of nature are the same everywhere, so there's no preferred location in space, leads to the conservation of the quantity called momentum, the motion of an object. Translation in time, the idea that there's no preferred zero of time, is connected with energy conservation. Rotational invariance, the absence of preferred direction in space, is correlated with angular momentum conservation. That's the famous example of a figure skater who draws her arms in and goes faster and faster because the combination of where the matter is and the speed at which it's moving is conserved. So these are all special cases of our first theorem for continuous symmetries. This was, to many people, a revelation at the time, precisely because people who developed the science of mechanics had built up the notions of energy and momentum and angular momentum over time, recognizing them as convenient quantities to measure, but without knowing that they had a fundamental basis. And through Netter's theorem, we're able to see that the success of these conservation laws has to do with regularities, the absence of changes in the laws of nature. One of her admirers was a theoretical physicist at Yale, Feza-Gurse, who was, among other things, a specialist in group theory and applying the ideas of Sophus Lee. And he wrote in the preface to her to her collected works, before Netter's theorem, the principle of conservation of energy was shrouded in mystery. Netter's simple and profound mathematical formulation did much to demystify physics. So what we know now, by virtue of this theorem, and the powerful aspect of her theorem is that it goes in both directions. You can start with a symmetry and find a conservation law, or you can start with a symmetry and look for the conservation law behind it, is that if we were, for example, to find a violation of the famous law of conservation of energy, that would be a strong hint, indeed, it would imply that there is something special about some time, that the idea of shifting in time without any inhibition would no longer be a true symmetry of the laws of nature. So that's one aspect of it. And as I say, this work is now fundamental to everything we do, and gives us a new way of trying to apply the old laws and understand them better, and also a way of trying to discern new laws of nature by doing experiments, making observations, thinking that we might possibly recognize symmetries in nature, and then asking how we could use those symmetries, apply those symmetries that we think we found in nature to either derive conservation laws, or, as we'll see in a few moments, to derive new interactions and compare the consequences of those new interaction laws with what we see around us. Now, part of the richness of nature is that not every symmetry that is present in the laws of nature is right out there for us to see. There are many symmetries that we call secret or hidden symmetries. And let me give you a couple of examples of those, because these are fundamental to many areas of physics: condensed matter physics, the physics of crystals, physics of elementary particles, and so on. So here's an example familiar to people in Chicago and in Stavanger, which is snowflakes. It's one of the first things that I think we're taught the word symmetry about, because we observe these objects. They have, many of them, a six-fold symmetry. They look almost identical when you take them and rotate them by 1/6 of a turn. And they are indeed beautiful. There are many stories about them that no two are identical and so on. They are three-dimensional objects, but we often regard them as two-dimensional objects. And you will see that for most of these, if we take a certain axis through the center of one of them and turn it by 1/6 of a turn, it looks, at least a very high approximation, the same. So that is one of our childhood encounters with the notion of symmetry. This was fascinating not only to you and me as children, and perhaps still as people of a certain age, but also to the famous astronomer and physicist Johannes Kepler, 16th century, 17th century scientist, shown here on the left. So there's good old Johannes. One of the things that you have to say about physicists of a previous generation is that they really knew how to dress in an impressive way. He was fascinated with geometry. You see that he has the famous tools of Euclidean geometry, the dividers and the ruler, in his formal portrait. But at a certain moment, when he was living in Prague, he too became fascinated with snow crystals, the snowflakes. But instead of just saying, "Oh, very nice, I look at them," and so on, he decided to try to apply his scientific reasoning to understand why they should come out in these shapes. And as a result of that, he wrote a little book, which has recently been reissued, called The Six-Cornered Snowflake, which he sent as a New Year's gift to one of his friends and future patrons, in which he tried to discern the reason behind it. He thought there must be some agent that did it. Well, it turns out that he was not quite right about that. There is no agent that does it. We learned only in the 1930s that the reason that the six-fold symmetry is favored is that water molecules themselves, the famous H2O, one hydrogen, two hydrogens and one oxygen, have the two hydrogens in, let's see, are we going to see this? Yes, there we are. Two hydrogen bonds are at an angle of 104 degrees, 104.5 degrees with respect to each other. And is that shape that makes them naturally fall together in the hexagonal shape, hexagonal symmetry that we see. He did suggest, without proof, that water itself seemed to flow and therefore didn't have a six-fold symmetry to it. And until we get down to the molecular level, that's a correct observation, because a water drop is like our perfect sphere. The droplet of water in the absence of gravity is a perfect sphere. It's an example of disorder. There's no preferred axis. As with our sphere, you can choose any diameter and turn it by any amount and it looks the same. So in the language of mathematicians, this is O3 symmetry, 3 dimensions, any axis, turn it by however much you want. The snowflake has a much reduced symmetry, which is called the dihedral group of degree 6, D6, which reflects the reflections around certain axes and the six-fold rotations that you can make. So this is an example of a law of nature, namely the laws of electromagnetism. And as I've said a moment ago, don't distinguish between left and right and up and down and forward and backward. They're completely, direction is arbitrary to them. But the consequences of those laws, as the water droplets are held together by electromagnetism, gives us this pattern that doesn't reveal the full symmetry of the laws of nature. So that's one example that is part of our everyday experience, at least in winter, in the places that you and I live. Here's another one. This has to do with a lump of iron that forms a magnet. This is a model of a magnet, which was published in the PhD thesis of a German physicist named Ernst Ising, who, when he moved to the United States, became Ernest Ising. So we'll give him his original name, Ising, here. And the idea is this. You can think of a lump of iron that becomes a magnet as having in each atom of iron a little needle or indicator that can point either up or down. So that's a simplification. We know that the real atom has a compass needle that can point in any direction. But often the key to understanding something in physics is to try to capture the essence of it in a slightly lobotomized version of it. So here's the idea. We use red for ups and blue for downs. And in a pattern, which is here made more or less random, and which you can imagine extending infinitely far in both directions, we have a random array of ups and downs, reds and blues. And we're going to make a theory in which there is no distinction, no preference for ups or downs. So that's shown here. You can even do this not with a lump of iron, but with a group of people and cards that have one red side and one blue side. We do it sometimes in classrooms just so that students can make their own hidden symmetry. So the idea is this, that you or one of our atoms is sitting at a certain point. Lost my pointer. Oh, there it is. So say you're sitting here. So you decide, what do I do next? And you look around you and you see what the neighbors are doing. If all the neighbors are blue, you turn blue. If a majority of the neighbors are blue, you turn blue. If a majority are red, you turn red. And if it's two reds and two blues, then you decide however you want what to do. And one way to do that is to flip a coin. So heads is blue, tails is red. And we can, of course, train a computer to do this. Normally, what we do is to apply these rules, but in a setting in which the temperature of the substance can be adjusted. At high temperatures, there's a lot of thermal motion, of jitter. And so superimposed on these rules is the tendency of things to just go wherever they want because of the thermal motion. That's the starting point that I have here. So there is Mr. Ising. Here is a random array at high temperatures in a very large array of these things. I've now made many more examples of the reds and the blues. And it turns out that this problem in 2 dimensions of how this model of a magnet developed was also solved by a Norwegian, Lars Ansager, who was a professor of chemistry at Yale when I was a boy, and who made a fantastically detailed mathematical solution about how this would behave. Well, we can go through all Mr. Ansager's equations, or we can tell, we could do this in a classroom with a smaller array, or we can tell computers to do it. So we tell computers to do it. We started out with our completely random array. We arrive at a place where we have a still random, but not quite random display as low temperatures. When this flipping around caused by thermal motion, thermal agitation becomes less and less important. And you see, we start to develop discrete domains of red and blue, ups and downs. If you cool further or run it further, these expand and become bigger and bigger. And eventually we get to a situation where it may flip all the way. And indeed, there's a strong preference for blue over red in this final figure. That does not mean that the original rules that we made up prefer blue over red, but just in this particular incarnation, this particular simulation, it happened by aleatory processes, by fluctuations, that the blues dominated over the reds. You can recover a notion of the symmetry by doing this experiment many, many times. And if all that I've said is true, you will get equal numbers of red outcomes and blue outcomes. And that is how we can tell that the symmetry was present in the first place. So here's a practical example. We can't get in and see the little compass needles flipping up and down, but we can hold a lump of magnetized iron in our hand. You could heat it up above 1080 kelvins, holding it carefully, of course, with something insulated, and cool it down again, and you'd see that it magnetizes in a different direction. So hidden symmetry number 2. Broken symmetries are a different story. So there are symmetries that are nearly there, but not completely there. Those are distinct from hidden symmetries. The first director of my laboratory, Robert Wilson, was an accomplished artist and sculptor, in addition to being a famous builder of accelerators. Here is one of the sculptures that he made for one of the entrances to the laboratory. It's called Broken Symmetry, and it has a number of interesting properties. One is that if you lie on the ground at the very center of it and look up, the 3 legs of it look perfectly symmetrical because you can't distinguish to the distances. So you're tempted to turn it by a third of a turn in every direction, then it looks the same. Here's evidence, by the way, that we do have snow in Illinois. If you look at it from this side, you see that it's not perfectly symmetrical. The different arms are offset by a little bit. And so it's an example of a broken symmetry. Symmetry is suggested, but not present. And if you were to look at it from the other side, facing into the laboratory, you would see that instead of being painted orange, it's painted black. So that's another explicit breaking of the symmetry. So artists like to play with these things, and I think all of us like to project the symmetries onto things and enjoy the departures from perfect symmetry. Okay, now I want to get to one of the applications of Emmy-Noether's second theorem, which has become extraordinarily important in the way we think about the basic forces of nature. In Chicago had a fire early in the 20th century that destroyed a lot of the downtown area, and that made it necessary to rebuild. This was just at the time that tall buildings, tall at that time meant maybe 10 stories, 20 stories, and then eventually higher, were coming into being. And so Chicago became quite a playground for inventive architects of the early 20th century. One of them was Louis Sullivan, shown here. And he was not only a designer of buildings and constructor of buildings, but also he had very definite aesthetic ideas and ideas about the utility of his buildings. He wrote a famous essay on the tall office building in particular, in which he coined the phrase that form should follow function in architecture and indeed in everything else, in which he advocated that a building was not there simply to be decorative or to celebrate the Greek and Roman forms of antiquity, but that it should respond to the uses to which the building would be built. And so his slogan was form follows function. Look at the function, we define the building's form by that. And one of the archetypes of that notion of architecture was a department store building that was called the Carson Peary Scott Building in Chicago. It still exists. It's now owned by the Target chain of department stores in more or less the original conditions, so they preserve the essential architectural features. So that's Mr. Sullivan and his way of thinking. You could turn it around. We could ask whether it's possible to turn it around. Is it possible that function should follow form instead? In our setting, what that question means is, could symmetries dictate interactions? Is it possible that by imagining that we recognize symmetries in the nature, there's some procedure we could follow that would turn those symmetries into theories of the fundamental interactions? First to try this out was our friend Hermann Weyl, who beginning in 1918, impressed by the successes of Einstein's theory of general relativity, asked whether he could make a unified theory of the two interactions that he knew at the time, gravitation, which had been known since antiquity and had been mastered by Einstein, and electromagnetism, which came into its present classical form in the middle to the end of the 19th century through the work of James Clerk Maxwell. And so he told a story. His story was that maybe it would be possible that at every separate point in space and time, you had the freedom to choose the dimensions of a ruler or the ticks of a clock, the intervals between ticks of a clock, and you could make a theory based on these. And maybe this would be a unified theory of electromagnetism and gravitation. So pretty ambitious. Turned out not to be right. There were some things missing for it. Poor Hermann came up with his idea before quantum mechanics had been invented. And so he was missing certain essential pieces. And it had other shortcomings, that it gave answers that depended on the path by which you traversed some trajectory. So it was wrong, but it was a really good idea. And in fact, in the same year is when Emmy Noether published her theorems. And the second of her theorems shows precisely how you would do this. It shows that for any continuous symmetry that you recognize in nature, you can make a mathematical construction that will lead to a theory that must have interactions of a certain form. So the good thing about that, from the point of view of physicists who want to build models of nature, is that whatever symmetry you have, you follow Emmy Noether's instructions and you can make a perfectly respectable mathematical theory. The downside, which is what Weil foundered on originally, was that because you can do this for any symmetry, there's no guarantee that the one you picked really corresponds to a law of nature. Well, after an interval of a decade and with some help from his friends, Weil recognized that if the symmetry that you apply, to which you apply this reasoning, is not something that we see every day in nature, but a rather arcane symmetry that has to do with phases of quantum mechanical wave functions, whatever that may mean, you could in fact derive the theory of electrodynamics, full content that Mr. Maxwell had labored over and that physics graduate students have trouble remembering. So I tell my students, should you be trapped on a desert island and you need to build a radio and you can't remember Maxwell's equations, you could just start with Weil's construction of electrodynamics. And then if you know how to operate wires and screwdrivers and things like that, you might be in luck. Anyway, that's a big breakthrough in the way that we think about things. So I say, for Weil's first try, it didn't work. Second try, it did work. And so we're motivated, or people were motivated finally many years later in the 1950s to apply this reasoning more generally. And the example that I'll give of that is one that I think Jumbo Kang will talk about in great detail on Friday. I'll just give you the briefest sketch of how that comes about. This is a guess that turns out to be correct. So we've learned through our experiments that protons and neutrons and other such things are made up of basic particles called quarks. The quarks, as far as we can tell, have no size. So they're very, very small, smaller than we can resolve. We idealize them as geometrical points for that reason. They have no internal structure, just there. A proton, roughly speaking, is made of 3 quarks, 2 up quarks and a down. The neutron is made of 2 down quarks and an up, where the up and the down have just the properties they need to make those statements true. And you can't make a consistent theory of the structure of a proton and neutron if you just say that. You have to embellish it a little bit by saying that each flavor of quark, up or down, the others we know about now, must come in 3 different species that, for no good reason, except it's convenient to draw pictures, we call colors. It's got nothing to do with color in the real world. It's just a label that we use. So I labeled them red and green and blue. You can pick your own favorite colors if you like. Now, you could just say, and originally this was the reasoning, Well, these give you a way of distinguishing the different kinds of quarks, and that makes everything fine with quantum mechanics, and you can describe the proton and neutron. But you can be bolder and say that the color satisfies a symmetry, and to say, we have no way of telling whether a quark is red or green or blue, and so these assignments are purely conventional. And once you've said that, you can follow the reasoning of Noether and Weil and the people who came after, and ask whether it wouldn't be possible to choose that location at each point in space-time. So I choose my convention here in Batavia, Illinois. You choose your convention in Stavanger. And for those of you who are visiting Stavanger, you can have a different convention everywhere that you go. So this is a little bit like having standards for navigation. All of us, when we talk about headings to go on an airplane or in a boat or every vehicle, generally refer our headings to north. True north, magnetic north, you choose it. And that's very convenient that we all have the same convention, because then if I could say my bearing is 280 degrees, you know exactly. But it's an accident of convention and maybe the fact that the Earth has a magnet inside it that we choose what we call north as the reference point. We could choose south-southeast as a reference point, and as long as we agreed on that, we could give our bearings with respect to that heading instead. So easy enough, we just have to all agree. But again, in the spirit of Noether, Weil, and followers, suppose we said, well, I'm going to have my convention and you can have your convention and so on. That would lead to navigational chaos unless there's some way of conveying your convention to my convention to my neighbor's convention and so on. And that gives a feeling for the content of Noether's second theorem, that there has to be, if you to do that, if you impose this condition on your equations, there has to be some force, some message carrier that moves from one place to another and carries the information so that we don't descend into chaos. We're able to build such a theory. It's a theory that's named quantum chromodynamics, where the chromodynamics comes from chromo of color. That is the theory of the strong force, and remarkably, although it was guessed by people, it turns out to be the true theory of the forces between quarks, the structure of protons and neutrons, and many more things that you'll hear about if you join on Friday. So that's a very quick description of the strategy that we use and one successful theory that comes about. Finally, I want to say a word about unobservables. Because all the interactions that we encounter in everyday life, mainly electromagnetism and gravitation, don't distinguish between left and right or up and down and forward and backward in terms of the fundamental interactions. It was long believed that the laws of nature should not be able to distinguish left and right. Two experiments done at the same time in 1957, studying weak decays, radioactive decays of an isotope called cobalt-60, its decay into an electron, and a nickel isotope, and the decay of the fundamental particle called the muon into electron and two neutrinos, both distinguished left and right. It was front page news in many of the newspapers around the world, here shown from the New York Times of the day after the press conference, with talk about communicating with people in an intelligent civilization on another world and being able to inform them of what we think of as left and right by looking at these things. Well, that was very dramatic. The famous physicist Wolfgang Pauli sent a sympathy card to his colleague Victor Weisskopf. Victor Weisskopf was my physics grandfather, as it turns out, in which he says, with the black border, "It is our sad duty to announce that our loyal friend of many years, Parity, the name for reflection invariance, went peacefully to her eternal rest on the 19th of January, 1957, after a short period of suffering in the face of further experimental interventions for those who survive her electron, muon, and neutrino." Well, to the physicists alive in 1957, who were physicists in 1957, this was absolutely something that turned the world upside down. The rest of us who learned about this in school maybe have become too accustomed to it to think of how truly remarkable it is and how it means we must have new ways of thinking about the laws of nature. In this case, we still do not know whether this is a fundamental asymmetry in the laws of nature or whether it's the result of a hidden symmetry that comes about in some way we have yet to determine, and that is one of the challenges before us. So I summarize, symmetry, as I'm sure you know from your everyday experience, going to art galleries, looking at the world, is a source of aesthetic pleasure, and it provokes our curiosity. For physicists, it guides us to understand nature and conceive new worlds. So both of these things are important, being able to solve problems in symmetry in nature and to invent new theories that may or may not be true. Unrelieved symmetry may be tedious. If you think of a world in which everything is the same, there's no distinction between this place and that place, may be perfect, but it may not be very stimulating. So it doesn't account for the diversity of our world and the change of our world. We are open to the possibility, in fact, many of us think it's likely that our universe began in a state close to or maybe at sublime perfection. And one of our challenges is to understand the sequence of hiding the symmetries that led us from that hypothetical perfect world to the world in which we find ourselves. We know many examples of hidden and secret symmetries. We think that the behavior of the weak interactions is such an example through the famous Higgs boson. In condensed matter physics, it's what's behind many of the most interesting phenomena. So one of the challenges for physicists is how do you look behind that veil and find out the symmetries that were there and what are the conditions that hide those symmetries. And our new insight, well, new since the 1950s, or new since 1918 when Nemi Noether first worked it out, is that symmetries seem to lie behind all the fundamental interactions: electromagnetism, gravitation, weak, strong, all of those we can call established conclusions. And maybe there are more, we speculate about more, and we think that they too may be derived from symmetries. To finish, let me invite you, I've given at the end of my slides a collection of decorative objects, and I invite you to spend some time with them and to see what different symmetries you can see in them, to ask yourself what makes them interesting to you or less interesting to you. If I go back to the dome and the Ludiskirche that we began with, I think that one of the things that is striking about this image, and you'll see it in many others that you look at, or things that you look at in museums or in decorative art of various sorts, architectural art, is that part of the richness of this is that not every element has the same symmetry. So for example, if we look at these red bands around the outside, well, that's a perfect circle. And you can turn that by any amount and it looks the same. But inside, there are elements that you can only turn by 1/16 of a turn or 1/8 of a turn or something else. And I would like to speculate, I'm sure that real artists have thought about this, whether explicitly or implicitly through the ages, that one of the things that makes an object like this very interesting to us and draws our attention is that there are so many different symmetries and patterns to recognize. So I invite you to look at that and make your own conclusions. And if you come up with a solution, please let me know, of course. Here's another example. This originated in the University of Stavanger webpage as a device that is there. You see reflection symmetry, or reflected objects. You see objects that are reflected and in which the colors are also reflected. So you can look at those, see what you see there. Here are some objects of decorative art from the famous architects of Chicago. So here's one, here's another. It's incredibly rich, and you see the presence of symmetry and the distinction from perfect symmetry is part of what makes them so interesting. And there we are. And here finally is a Persian rug, in which you will see a symmetry, or at least an approximate symmetry, of changing the scale of the objects on the outside rather than just doing rotations. So there are all manner of things that you can use to invoke symmetries or samenesses or resemblances. With that, the last one. So this is for everybody, but especially for physics students in the audience. Here is a simple representation of what we take to be the fundamental particles of our time, the 6 quarks and the 6 leptons, particles that have strong interactions and particles that don't have strong interactions. These are the family patterns that we think they have. So color symmetries, family symmetries, things that maybe stand apart for each other, maybe come together. And I invite all the physics students to see what symmetries you can imagine, what interactions you would imagine, how you might do more to put these together and to give us a more comprehensive understanding of nature. And with that, let's hope that by this time next year, there might be a real physical conference and we might be all together in Stavanger. Thank you very much.
Thank you, Chris, for this really insightful and at the same time quite entertaining presentation. I myself, I enjoyed it a lot. We already received a few questions from the audience, and I would just like to go through them with you. So we had a question by Unhi, and she wrote, you mentioned that Emmy Noether's work was first not recognized somehow as relevant.
Sorry.
And only after 30 years or so, one understood
Alexander,
what one could do with it.
Phone call came in and blocked our WhatsApp
asked,
call.
Does this
So if you could
happen
reconnect.
more often, or was this just a singular instance in the history of physics?
If you could reconnect on WhatsApp or possibly send me the
I will have to reconnect to
questions
our
in the chat
speaker.
because we got cut off. Oh, here you are coming back. I think we're reconnected, yes? Okay.
Very good. Yes, now we are reconnected. And I don't know until when our connection remained. Did you hear me
No, I did not.
Asking the first question?
Scam phone call came in.
Okay, then I see. So I will read the question again and ask you for an answer with the synchronization 5 seconds delay. Thank you very much. So again, let me read the question by Unhi. She asked, you mentioned that Emmy Noether's work was first not recognized as somehow relevant, and only 30 years later, one understood what it could be used for. And she now asks, does this happen more often, or was this some singular point in the history of physics that people didn't
I think
see
there were
what was coming?
A number of causes. It does happen frequently for all of us that we may hear something and not be prepared to make use of it or to take advantage of it. We have to be prepared before we recognize that something is relevant to what we're thinking about. In the case of Noether's work, it is certainly complicated by a number of factors. She was at the time in Göttingen. Göttingen was also a hotbed of the development of quantum mechanics a few years later. And so one explanation is that the physicists, although they were in close touch with the mathematicians, had this fantastically exciting stuff to do. They're inventing whole new fields of science, understanding the atom, all of that. And so they just had a full plate, as we would say. The second is that after doing this work, she turned to the kind of research for which she is truly famous in the mathematical world in what's called modern, or what has been called modern algebra. I think the modern is dropped now because it's incorporated as what people understand to be algebra. She's known as the mother of modern algebra, and in the 20s and into the 30s, she was developing a whole school and a bunch of followers who were doing that. So she never made applications of it. The other thing, which is perhaps more subtle, is that the real strength of these applications, as we make them today, come from applications to what we call internal symmetries, things like the color symmetry or the symmetry, the family symmetry between up and down quarks or electrons and neutrinos. Those didn't exist yet. So isospin, the first of those, the resemblance between the proton and the neutron, or the up and down quark, wasn't recognized as a conjecture even until the 1930s because the neutron hadn't been discovered. And it was Werner Heisenberg who first made that conjecture that there could be a symmetry that related those things. Heisenberg, in an interview or a discussion with his disciples late in life, confessed that he had never read Noether's paper. Again, people were busy doing what they were doing. Hard to criticize Heisenberg for not having done enough for physics, nuclear physics at the time. So I think it's a combination of things of that sort. And one thing for all of us to ask is, what's the good idea that we heard last week that we said, oh, well, that's no value to me. I'll think about it some other day. And to try to pay attention to what our colleagues are doing. So pretty interesting.
That's really food for thought. What are the ideas that we are somehow not yet picking up on that will become relevant in 20 years? Indeed. Then he has a second question to the later part of your presentation, namely when you were talking about magnets. She asks, when you talked about changing the temperature, and does this mean that temperature can destroy a magnet?
So if we take a real magnet made of just a lump of soft iron, it will spontaneously magnetize at a low temperature. Often when we have a magnet, it's something to which a magnetic field has been applied. And so it's been oriented in a certain direction. But if you take a big bulk, it will just orient spontaneously in some direction or other. And indeed, for soft iron, the magic temperature, the critical temperature, or the Curie temperature is 1080 kelvins. If you heat above that, then the random motion takes over and just gives you a random orientation of the magnet, so that in any small volume, any finite volume within the magnet, the net magnetization is zero. And then if you let it cool down, the whole thing will again magnetize either into domains or maybe into a one orientation in which there will be a spontaneous magnetization. And you can calculate this as part of what Lars Ansager did in the two-dimensional model. You can calculate what the degree of magnetization will be at any particular temperature. So it's when personal computers were new, I bought for my children, I said, an Atari 800 computer, which was one of the first in which you could do things. And the first thing I did was to simulate the two-dimensional Ising model. And it's quite fascinating because you can tune the temperature. I can send you a link to a very nice simulation in which you can play these games yourself and see how changing the temperature changes the outcome. And so I will do that. You can put it on the YouTube site. The thing that I learned, I'm very sophisticated after all. I'm a theorist who spends all his time with experimenters, and so I really understand statistics. You might think, I certainly thought. But what I learned from doing those exercises late at night for hours at a time is that even those among us who claim to be sophisticated, sort of narrow distributions, we think that things should be very close to the mean, and that fluctuations that are far from the mean seem to us totally not possible. Well, it's not that they're not possible, it's just that they're improbable. And there's a famous ancient saying that it is a part of probability that very improbable things are possible. They're not only possible, they're required. So yes, you can do that.
Very nice. Thanks. Yeah, we will surely share the link to these simulations in the description of the video. Let me also ask something, because I was really inspired when you showed this pattern from the ceiling of the church in Munich, because it reminded me that you can apply different type of symmetries after another, and this pattern stays the same. So you can rotate it first, say 90 degrees, then you flip it, and you might rotate it by another angle, and again you will get the same pattern. And that reminded me that you told us that there are some symmetries in nature that died in 1957, but there seems to be a supersymmetry. No, I shouldn't say supersymmetry, but there is a special type of symmetry in nature that so far has survived any attempts of finding it to be broken, and that comes from doing three symmetry operations on our physics theories after each other, like rotating it first, flipping it, and then rotating it again. And somehow physics, as far as we know, is always looks the same after we do these three symmetry operations. Do you have any thoughts on will we ever see this special type of symmetry, this so-called in technical terms CPT symmetry of nature, ever to go the way
So
of
there are,
parity alone?
you evoked many things, and I'd like to talk about a couple of them. One of them is that the CPT symmetry, particle into antiparticle, reflection symmetry, time reversal symmetry, all taken together, we do not know how to formulate a theory that doesn't respect those three taken together. So it's very important to test that symmetry, because if we were to find a violation, we would have to revise the way we think about theories of nature in a very fundamental way. That would be frightening, but it would also be very stimulating. There'd be something to learn from that. So those experiments to test that combined symmetry are going on all the time in many different arenas. And we thought, we think we know the answer will be, well, of course, that symmetry is respected, but maybe it will turn out that that's not true, and that would be big news indeed. Now, you talked about the decorative symmetry and the fact that you could rotate and reflect, or reflect and then rotate. That's a very important property of those. We call such symmetries abelian, named after Niels Henrik Abel, precisely because the order in which you do them doesn't matter. And we've attributed to him the extensive study of those kinds of groups. Also, symmetries, the color symmetry is one of them, for which the order in which you do operations does matter. Now, I don't think I can do this on the camera, but here's another exercise that you can try to do at home. Let's see. Okay, so here is a book, a notebook. And what I'm going to do is to rotate it this way and then turn it up. And if you look at it, you'll see that the back of the book is facing me and the long edge is on top. I can start in the same place, and I can turn it upward first and then rotate it, and I get a different answer. Now the front of the book is facing me, and the spine of the book. Sorry that we didn't think about doing this right. Anyway, those of you who happen to have a book before you or can find a book, I invite you to do little exercises in which you do 2 or 3 operations that are the same, but do them in different orders. And you'll find that those do not commute, as we say, that the order matters. And that's a very important characteristic of theories like quantum chromodynamics. It is responsible for the distinction between quantum chromodynamics and electromagnetism. And when you get into the guts of the theory, one of the things that is different is that the force particles of quantum chromodynamics, the particles we call gluons, interact among themselves, whereas photons in electromagnetism do not interact among themselves. And that comes down to the question of whether the symmetries involved are abelian or non-abelian symmetries, those for which the order matters or doesn't matter. So you got something very deep.
Perfect. Thank you very much for these answers. I do not see any further answers in the chat. I think everybody is just digesting all the things that they heard about today. And with that, I would just like to invite our audience to remember that there is a third presentation coming up this Friday, August 6th, where we will hear about the strong force from Zhongbo Kang, and we hope to see you there. Chris, thank you again for your presentation.
Thank you.
And good night, everyone.